If we're working with weak bases in an equilibrium, we're given Kb values. If we're given acids, we're given pKa values. The relationship between those is very similar to pH and pOH. So if we know that pH and pOH added together to the sum of 14, pKa and pKb also give us the sum of 14. So just a little interchange. The word P is negative log of hydrogen ion, negative log of hydroxide ion. When added together give us 14. That relationship also holds true for the Ka and Kb values, P's. So another just eye opener, maybe a little easier solutions if you're being asked to solve from one to the other. Alrighty. So let's take a look here. I'm going to grab a clean sheet, work this out on one sheet instead of many. Here's an example where this time we have a base, notice the Kb value, is in equilibrium with its conjugate acid, ammonium chloride. Same problem, we're just kind of shifting from weak acid and its conjugate base to a weak base with its conjugate acid. Ammonium chloride is a salt. It 100% dissociates. It will not have an equilibrium. The equilibrium here is coming from the weak base. So let's take a look at what we know. A weak base, such as ammonia, when placed into water, sets up an equilibrium where its conjugate acid and base are in equilibrium. Ammonia and water make ammonium and hydroxide. See, the common ion is the ammonium ion. So a weak base has a conjugate acid. A weak acid has a conjugate base. They both have a common ion. They have the same first name in common. So the common ion here is ammonium and its conjugate acid of the base ammonia. The other thing we know is that pKb is equal to 4.75. We know that 0.5 moles of ammonia is placed into a solution with 0.2 mole ammonium chloride. The common ion is 0.2 mole for ammonium, 0.5 molar for ammonia. We'd like to know the pH. Let's give the value X the value for hydroxide. Just the expression, just to get us back in gear. We're going to take pKb, and what that is given to us as the concentration of products over reactants. So let me just even take this off, back up even further. Kb is an expression, and I'm no numbers, but to just help us put it in place. Ammonium times hydroxide all over the concentration of ammonia. Alrighty. So Kb is the expression of products over reactants. Coefficients become the powers with which they're raised, all ones in this case. We have a pKb, but in this expression we need it to be a Kb. All right, no problem. 10 raised to the negative 4.75 is how I flip a pKb back to Kb. That's going to be set equal to the concentration of 0.2, that's the ammonium ion, times the concentration of the base, X, all over the reactant, 0.5. Let's solve for X, knowing that that's representing hydroxide ion. Alrighty. 10 raised to the negative 4.75 turns my pKb into just a plain old Kb. I'll cross multiply times 0.5 and divide by 0.2, and I pull out X. And that gives me 4.45 times 10 to the negative fifth molar units. When I negative log hydroxide, I get something called pOH. So I'll hit negative log of my answer, and pOH is 4.35. Not done, because they want to know pH. Systems are reported with the hydrogen value. 14 minus that answer flips my POH into a pH, and that value is 9.65. Makes much good sense for a base. It's above 7 for a pH range. 9.65 pH units. We took a base in equilibrium with its conjugate acid, products over reactants, subbed in, just assuming the 5% rule, subbed in the values, solved for X. The concentration of hydroxide was then used to calculate POH, which was then flipped to a pH unit 9.65. Let's flip ahead and see how close, right here, 9.65 pH units. Perfect.